welcome to the course on biostatistics and design of experiments. We will continue on Anova. We will look at one more problem. This is a 3-way Anova, okay, and there is a possibility of interaction also in this 3-way Anova, but the number of experiments done is not sufficient actually. Okay. Imagine I am doing a process optimization of a bioprocess. This is very common. We do a lot of process optimization where we modify the carbon concentration or even carbon source, nitrogen, then type of organism, agitation, temperature, micronutrients, pH and so on. So, imagine a problem, it is a 3-way Anova, that means I have 3 independent variables or 3 main effects as we call it, the carbon amount, the nitrogen amount and the reaction time. These are the 3 variables or parameters or effects I am modifying, and I am measuring the final product yield. Okay. This is called a full factorial experimental design at 2 levels. That means I am looking at say carbon concentration at one level and another level. That means it could be say 5% carbon and this could be 8% carbon, but I have put it in a coded form. Normally when you plan the designs we always put them in coded form. We will talk about it later, the coding and all that. But so at 2 levels of carbon concentration, A0 and A1, at 2 levels of the nitrogen concentration B0 and B1, at 2 levels of reaction time C0 and C1. So, if I have 3 parameters and I am changing each parameter in 2 levels, that means 2 into 2 into 2, that is 8 experiments. So, I have done 8 experiments. I have not replicated anything, but I have done 8 experiments and each one at 2 levels, and this is called a full factorial experimental design. Okay. 2 into 2 into 2, that means 2 raised to the power 3. So, I have full factorial experimental design in this particular situation. Okay. So, 3 parameters and 2 levels, A could be carbon concentration, B could be nitrogen concentration, C is the reaction time. So, I am getting some product yield here mostly in grams per liter, this is the amount. Now, I want to look at it, look at the main effects and see whether I can even get interaction effects, but that is going to be a bit problematic, you will see why, okay, as we go along. Okay, so pictorially how do they look like? So, A0, A1 like this, then I am changing B0, B0 here and B1 here, and at one particular concentration value of C0, that is reaction time. So, at one reaction time A0 changes like this, A0 to A1 and this is for another B. Now, at another C1 we have another picture like this actually, okay, like this, right, A0 A1 like this, and this is for A0 A1 at B1, okay, at this is at B at one value of B and that is at another value of B, that is B0 and B1, okay. So, we have it is always good to drop figures because sometimes figures always show as things like interactions and how the performance is pictorially. Okay. So, we have 8 experiments. So, we can do an Anova, we can get a total sum of squares, we can get sum of squares for each of the main effects. We can get a sum of squares for A, we can get a sum of squares for B, we can get sum of squares for C, then we can get a total sum of squares also. Okay. Let us go further as usual. So, again I am showing you this picture. So, average A0 will be this plus this plus this plus this divided by 4. Average A1 will be this plus this plus this plus this divided by 4. Average B naught will be this added divided by 4. Average B1 will be this plus this plus this plus this divided by 4. Average C naught will be add all these 4 divided by 4. Average C1 will be add all these 4 divided by 4. Now, the global average could be average of any one of these 2 or these 2 or these 2. I should get the same answer. So, the global average is 5.45, very simple. Now, let us look at the sum of squares for A. How do you know? You know how to do that, right? So, there will be there are 2 levels for A or 2 groups for A. So, you will get 2 sum of squares term, okay, okay. So, we have 2 levels for A. So, how do you get this for A? What we do is we take this 4.8 minus 5.4, okay, square it up and then multiply by 4. Why 4? We have here 4 values for A, and then how do you get this? What we do is average of A1 is here, global average is here, subtract one from another, square it up, multiply by 4. Now how do you do for B? B naught 7.87 minus 5.445, square it up, then multiply by 4. Okay. Then for the other one 3.02 minus 5.45, square it up, multiply by 4. Now let us look for C, 5.15 minus 5.45, square it up, multiply by 4, and then 5.75 minus 5.45, multiply by square it up, then multiply by 4. So why did I say 4? Because for A naught we have 4 terms, for A1 we have 4 terms, for B naught we have 4 terms, for B1 we have 4 terms, for C naught we have 4 terms, and C1 also 4 terms. Okay. So when you add each these two, we will get sum of squares for A, sum of squares for B, sum of squares for C, straightforward. Now how do you get the total sum of squares? So each of the term we subtract from 5.45, square it up. So this 7.2 minus 5.45 square and so on. So we will get 8 terms here. You add all of them, we will end up having a total sum of squares. Okay. So now we can assume the error is equal to total sum of squares minus SS minus SSB and SSC. That is one way. If I am interested in looking at interaction, imagine I am interested in looking at interactions. So what do? I can look 2 at a time, because here I have 3. So I can look 2 at a time. That means first I will look at AB. So I can take an average of C0 and C1 and put it here. Okay. So I can look 2 at a time. Okay. Let us look at again, this is my the full factorial design experiments. Okay. So what do? I take C's average route 7.2 plus 6.7 by 2, 8.4 plus 9.2 by 2, 2 plus 3.4 by 2, 3 plus 3.7 by 2. So I have now a 2 effect problem where C is averaged out. Okay, understand? So 2 effect problem. So again I can do a sum of squares. So average of A naught will be 6 this plus this divide 2 for okay, average of A naught this plus this divided by 2, average of A1 this plus this divided by 2, and of course if you go to the previous so if you go to the previous one, you should be getting the same 4.825 and 6.075. Okay, so 4.825. So you should get the same thing. So average of B naught will be this plus this divided by 2, average of B1 this plus this divided by 2. Okay, so we got the averages for these, and then global average will be again you should get 5.45 when you add up all these 4 items divided by 2. Now we can do a sum of squares for A, sum of squares for B, and then total sum of squares. Okay, for A what do? 4.825 minus 5.45 square, 6.075 minus 5.45 square, and you have to multiply by 4 each term. Okay, do not forget that. Okay, because we have here 2 terms, and getting this again taken from average of 2 terms. So 4. Okay, so sum of squares for A is 3.125. Okay, so if you look at it, the previous one, sum of squares for A, in fact it is coming out to be it will come out to be the same, and same thing for B, we will get 47.045. How do you get this term? This minus this square multiplied by 4, this minus this square multiplied by 4. So we get B here. Here there is no C because you have taken averaged out, but your total sum of squares will be different from the previous case. Okay, total sum of squares will be different from previous case. Here 52.56, but here you will get it different because the terms here are different here. Okay, how do you get that total sum of squares? There are 4 terms here. When we take the 5.45 minus 6.95 square multiplied by 2, then we take 5.45 minus 2.7 square multiplied by 2, then we take 5.45 minus 8.8 square multiplied by 2, then we take 5.45 minus 3.35 square multiplied by 2. So, you will get 4 terms, you add all of them to get the total sum of squares. So, you can subtract the sum of squares of A, sum of squares of B from this 50.89, that will be the error, or we can even say that is the interaction between A and B. So, we can call this as AB sum of squares, that is the interaction between A and B, which comes out to be 0.72. Okay. So, interestingly, if you look at it, the degrees of freedom for A will be 1 because we have 2 levels for A, degrees of freedom for B will be 1 because you have 2 levels for B, and the total degrees of freedom here is 3. So, AB will have 1 degree of freedom. So, either you call it error or you call it AB, only one you can call it, because you cannot call both AB as well as error because you do not have sufficient degrees of freedom here. So, we call this as AB, which is 0.72. Okay. So, we from the previous figure, from the previous table, we got the okay, sum of squares for A, sum of squares for B, sum of squares for C, total sum of squares, and then from the next one we got sum of squares for AB here. Okay. Now, same thing we can do for other 2 variables. Here we can take B as averaged out. So, what do? We will have A naught A1 in one column and C naught C1 in the other one. So, how do you do okay? How do you do B averaging out? So, that will come out to be 7.2 plus 2 divided by 2, okay? 8.4 plus 3 divided by 2, okay? 6.7 plus 3.4 divided by 2, 9.2 plus 3.7 divided by 2. So, B is now averaged out. So, we have a table for A naught A1 here and C naught C1, just like the previous one. Here we have A naught A1 here and C naught C1 here. Okay. So, again we can do the same thing, we can get average of A naught, that is this plus this by 2, average of A1 this plus this by 2, okay, average of A1 this plus this by 2, okay. Then average of C naught this plus this by 2, average of C1 this plus this by 2, then global average will be average of the entire lot 5 point. Okay. Then now we can get the sum of squares, we can use this or we can take it from the original main effect table also. But so how do you get this particular term? We take 4.825 minus 5.45 square multiplied by 4. How do you get this term? 6.075 minus 5.45 square into 4. How do you get this term? Okay, 5.15 minus 5.45 square multiplied by 4. How do you get this term? 5.75 minus 4.5 square multiplied by 4. So, sum of squares for A is 3.125, sum of squares for C is 0.72. Now, this will be the same as the original okay, 0.72. Okay. So, you should be getting the same answer actually, okay, 0.72, sorry, this is 0.72. So, the total will come out to be different, of course. So, how do you get the total? We have to subtract each one of these items, do not go here, but go here, okay, the reduced table with 2 with 2 parameter table. So, 4.6 minus 5.45 square, 5.05 minus 5.45 square, but please remember, okay, that here you have to multiply by 2 because each one of these term is made up of 2, okay. Then 5.7 sorry 5.7 minus 5.45 square multiplied by 2, 6.45 minus 5.45, okay. So, when you do that and add up, you will get this as your total sum of squares for this reduced table, okay, for the reduced table. So, we can do total sum of squares minus sum of squares due to C, sum of squares due to A, and either call it as an error or we can call it as a sum of squares for AC, okay, sum of squares for AC, that is AC interaction. And as I said before, A will have 1 degree of freedom because A has 2 levels, C will have 1 degree of freedom because C has 2 levels. So, AC will have 1 degree of freedom, and there are 4 experiments. So, 3 degrees of freedom you are showing here. 3 degrees of freedom means if the main effects take 1 1, so either you can have error or you can have a interaction AC, we cannot have both, okay, we cannot have both error as well as interaction. So, this is the interaction AC, okay. Then we go to the next one where we have BC and A is averaged out, okay. So, we have BC and A is averaged out. So, how do you average out the A? Okay. So, we have this table. Now, what we do is we take okay, the A gets averaged out, okay. So, we combine, add these two, divide by 2, add these two, divide by 2, 2 plus 3 by 2 is 2.5, 7.2 plus 8.4 divided by 2 is this, 7.8, 6.7 plus 9.2 divided by 2 is 7.95, 3.4 plus 3.7 divided by 2 is 3.55. Okay. So, now we have a reduced table with only B and C, A is not there. So, we will get an average of C naught here, which is this plus this by 2, average of C1 here, this plus this by 2, average of B naught, this plus this by 2, average of B1, this plus this by 2. The global average will be average of any two of these, okay, any two of these, C naught C1 or B naught B1, like that. So, we will get 5.45. This is the same as the original value. Now, how do you do the sum of squares for C? Simple. So, we have 5.15 minus 5.45 square multiply by 4, do not forget we have to multiply by 4, then 5.75 minus 5.45 square multiply by 4, then we have 7.87 minus 5.45 multiply square multiply by 4, 3.02 minus 5.45 square multiply by 4, okay, 4 here, okay. Now, if you add these, you will get sum of squares for corresponding to C. If you add these, you will get sum of squares corresponding to B here, okay. So, quite simple. Now, how do you get the total? Total is 7.8, okay, yeah, 7.8 minus 5.45, okay, square it up and then multiply by 2. Do not forget, for the total sum of squares we are multiplying by 2 because each one of these term is made up of 2 terms, right. Like I said, if you want to take this particular term, okay, I am adding this plus this by 2, 7.2. So, this itself is made up of 2, that is why for total sum of squares what do we do? 7.8 minus 5.45 square multiply by 2, okay, and so on actually. 2.5 minus 5.45 multiply by 2, okay. 7.95 minus 5.45 square multiply by 2, 3.55 minus 5.45, okay, multiply by 2. So, we get these 4 terms, add up all of this will give you the total sum of squares. So, from total sum of squares we can subtract sum of squares for B, sum of squares for C, and that will either we call it error or we call it sum of squares due to BC. As I said, C has 2 levels, so DF is 1, B has 2 levels, so DF is 1, and total you have 4 experiments, so 3 degrees of freedom. So, you have one extra DF which we can be calling it as error or we can call it sum of squares due to BC, okay. Okay, so, this is how we have done. We have calculated the main effects, and then we have calculated the interaction effects AB, AC and BC, okay, and we also have the total sum of squares which is given by the 52.56, okay. So, here we have the sum of squares because of A, main effects is called, sum of squares because of B, sum of squares because of C, and this is the total sum of squares. So, it may contain everything. Then we have we got a AB sum of squares. How did we get the AB sum of squares? What did we do? We averaged the C here. So, what did we do? We just made a B and A table, C is averaged out. So, 6.7 plus 7.2 divided by 2, 8.4 plus 9.2 divided by 2, 2 plus 3.4 okay, divided by 2, 3 plus 3.7 divided by 2, that is what we got. So, then we did an average for A naught, average for A1, average for B naught, average for B1, global average. Okay, then for A what did I do? 4.85 okay, minus 5.45 square but multiplied by 4, 6.075 minus 5.45 square multiplied by 4. Why 4? Because each of these terms is made up of 2 and each of these is also made up of 2 from the original table, that is why we are multiplying by 4. Now, when so you get sum of squares for A, sum of squares for B. Now, how do you get the total sum of squares? We again as you know, this is your table. So, 6.95 minus 5.45 okay, 6.95 minus 5.45 square, but do not forget you need to multiply by 2 because the 6.95 is made up of average of these, right. So, you get this. Then 8.8 minus 5.45 square multiply by 2, 2.7 minus 5.45 square multiply by 2, 3.35 minus 5.45 multiply square multiply by 2, that will give you total sum of squares here, do you understand. Then you can subtract TSS minus you can subtract SS of A, SS of B from TSS to get either we call it error or we can call it interaction AB, that is what I mentioned here. It will have 1 degree of freedom because A has 1 degree of freedom, B has 1 degree of freedom. So, same thing we can do, just like averaged out C to get a table for AB, I can average out B to get a table for AC. Okay. So, once I do that, I do the same calculation. Do not forget when I am calculating the sum of squares for A, I will multiply by 4, C also I multiply by 4, but when I am calculating the total sum of squares I will be multiplying by 2. Okay. So, here I will get the average for A naught, average for A1, average for C naught, average for C1, global average. Then for A, how do I get it? This minus this square multiplied by 4. Okay. Then how do I get total? I will take this 5.45 minus 4.6 square but multiply by 2, do not forget this. So, I will get 4 terms which I add up to get total sum of squares. Now, when I subtract each of these effect A and C from TSS, I will get AC, or I can call it error also, but I will call it AC for the time being, but it will have 1 degree of freedom. Then after that I make a table for B, C where I am averaging out A. So, how do I average out A? I will take this plus this, add up, divide by 2, okay. This plus this, add up, divide by 2. So, that will be column for C naught and row for B naught. This plus this, add up, divide by 2, okay. This plus this, add up, divide by 2, that will be column for C1. So, A is averaged out, understood. So, we have the average for C naught, average for C1, average for B naught, average for B1, then global average. Now, for C, when you are calculating sum of squares, what do you do? 5.45 minus 5.15 square multiply by 4, okay. Same thing here, okay. Then B 7.875 minus 5.45 square multiply by 4. Then for this 3.025 minus 5.45 square multiply by 4. Now, here how do you do? 5.45 minus 1.8 square multiply by 2, okay. 2.5 minus 5.45 square it up, okay, then multiply by 2 here, do not forget. then 3.55 minus 5.45 square, okay, multiply by 2. Then you add up all these 4 terms together, that will give you total sum of squares. So you subtract sum of squares due to effect C, sum of squares due to effect B, and that should give you BC. Okay, now we can go for our ANOVA table. This is our ANOVA table. We have the main effects A, B, C, sum of squares you have written down. Now I picked up the AB, AC, BC. So if I subtract the total from each one of them, okay, if I subtract the total from each one of them, I should get error. Okay. So I add up all these things, subtract from 52.56, that will give you 0.5. How did I get this 52.56? That is the original one, if you remember, original table, understand, original table, that is the total sum of squares. Okay, now totally I have done 8 experiments, 2 into 2 into 2, so 7 degrees of freedom. A has 1 degree of freedom, B has 1, C has 1, AB has 1, AC has 1, BC has 1. So if you add up all these and subtract from 7, you will get 1 degree of freedom. Error is coming out to be 0.5. So how do you calculate it? I mean sum of squares, okay, divide by the DF, so you will get this. How do you calculate F? You divide 3.125 by 0.5, 47 by 0.5, 0.72 by 0.5, 0.72 by 0.5, 0.045 by 0.5, 0.45 by 0.5, 0.8. Okay. So this is the F ratios. Now let us go to the table for 1 degree of freedom, 1 into 1, 1 comma 1, okay, 1 comma 1 for a 95% we get 161.45. Wow, that is a big number. So obviously we end up saying that none of the main effects or even the interaction effects are significant. Okay. Now because the interaction, once I said that interaction can even be considered as error, okay, we can add all these into the error, all these into the error, okay, all these into the error. So 3.125, 47.05, 0.72, 111, because each of the main effects has 2 levels. Now I can add all these interactions with the error, so the error will have 4 degrees of freedom because total experiments is 7, each of the effects has 111, so 4 degrees of freedom. So when I add up all these, I will end up with the error as 1.67. Okay, so mean sum of squares divided by 1 divided by 1 divided by 1, here it will be divided by 4, so 0.415. Okay, so 3.1 divided by 0.4 is 7.4, 47 divided by 0.4 is 112, okay, and then 0.7 by 0.4 is 1.7. Now if you go to F table, the degrees of freedom is 1 comma 4, okay, so 1 comma 4, so it comes out to be 7.71. When you do that, we see that effect, the main effect B is significant, okay, because the F calculated is larger than the F from the table. So B is significant, that means nitrogen seem to have a significant effect in the metabolite production actually. Now A is not really significant because it is 7.48, but it is closer to 7.71, so you better do more experiments to see whether it is really not significant or is it statistically significant. So because it is sort of closer to that. Okay. So you understand this problem, it is quite an involved problem. We have 3 parameters A, B, C, these are called the main effects, and then so obviously there could be interaction A, B, A, C, B, C type of interactions are possible. So but the number of experiments are less, that means you have not done any replications, so total number of experiments are 7. So if A, B, C take away 1 DF, so we are left with only 4 DFs, and if we want to calculate A, B, A, C, B, C, then we will have 1, 1, 1, so error will end up having only 1 degree of freedom. Okay. So when we use that approach and calculate F values, we see none of them are significant. But then these interactions are anyway not significant or very small, so we can combine that with the error. So what happens, DF for the error goes up to 4, and we have to add up all these with 0.5, so this comes out to be 1.67. So F ratios change to to 7.48, 112, 1.7. But the main thing that happens is now we are looking at the table at 1,4 degrees of freedom. So, the number has gone down dramatically to 7.71. Okay. Then we see that main effect B is significant. Okay. Main effect B is significant because it is 112 at 95% or okay, even at 99% it is significant, right. And main effect A is not significant as per this table comparison, but still 7.48 is closer to 7.71. So, you better watch out, do few more experiments to confirm whether to accept the null hypothesis or reject the null hypothesis. So, in this problem we had possibility of interactions being measured, but then our error df is very low, only 1 degree of freedom, because we have not done any replications of the experiments. If we had done a lot of replications, then we might have had a better chance of seeing interaction effects. But here, because we did not do much of replications, either we can call all these interactions into error, or we can try to put them each separately. But when we tried that, it does not work out, because error ends up having only 1 degree of freedom, whereas when we combine all these together and put them as error, then error gets a higher number of degrees of freedom. So, we are able to see some main effects being significant as against this particular Anova table, where none of the main effects are significant. Do you understand this problem? It is very interesting, very extremely interesting problem, where in a bioprocess or even in drug discovery, drug testing, you will end up having interactions, and if you want to see the interactions, the degrees of freedom for error goes down so dramatically that you are not able to really see clearly the effect of each of these parameters. So, one of the takeaway here is error should have sufficiently large degree of freedom. It cannot be so low as 1, that is one thing. Other thing is if you have a 2 by 2 table, and if you have not replicated, then the chance you can either call it interaction or you can call it error, because the degrees of freedom are much less. Okay. So, that way this problem is extremely interesting, and also I taught how to reduce from a 3 by 3 type of table into a 2 by 2 table by taking average of for each variable. So, when we had A, B, C in 2 levels, 8 experiments, what we did, we made a table of A and B alone by taking averages from C, and then later on we had A and C alone by taking averages of B. Then later on we had B and C alone by taking averages of A. So, okay. So, every time we reduced it to 2 by 2 type of table, and we looked at the interaction effects also. Okay. So, we will continue again in the next class on some other topic. Thank you very much.